And so I'm going to turn it over to Dan. Dan Mecklenburg is with the Ohio Department of Natural Resources, the Division of Soil and Water Resources. And he and his colleague Laura Fay have produced a report, Functional Assessment of Stream Restoration in Ohio. And I've asked Dan to talk about that report, mostly to get people interested in it and going and looking at it. So I hope this isn't just a substitute for looking at that report. I hope it will encourage folks to go and take a closer look at it. But Dan's going to give us an overview of it and hopefully answer some questions from you folks out there. So Dan, I'm going to go ahead and turn it over to you.
Thanks, Joe. Good afternoon. As Joe mentioned, I'm going to talk a bit about stream restoration in Ohio. And we've been at this now for a while. I can see some of the names on the list, familiar names that have been at it for a while, along with myself and Laura Fay. And it's probably not a bad time to be looking back and seeing how we're doing, the intention of this report. And this report isn't alone in that timing either, that while we've been doing channel work for centuries, it's just really been just over a decade that we've been trying to construct channels, do channel work so that we're restoring some of the function that we see in natural streams rather than just the single purpose of channel work has done in the past. And trying to slip in a definition of stream restoration there, that it's restoration of the functions rather than trying to restore it back to pristine conditions, pre-settlement conditions. Anyway, we're certainly not alone in doing that. I've seen a number of reports coming out in similar kinds of timing as this one from around the country and even around the world. I think the last one I saw was out of Denmark. I've seen another one out of New Zealand. So I think the stream restoration industry is now up and running and kicking out a number of projects, enough projects that are now old enough that we can go back and see them. It's certainly not like cars where we can test their performance right off the assembly line, because streams are streams and dynamic and influenced by big episodic kinds of events that taking a while and waiting for the numbers of them to accumulate is what we've done and what people have done elsewhere as well. If I can get these. There we go. The Division of Soil and Water Conservation, Division of Soil and Water Resources, is involved in this. We've been involved in stream restoration over the last decade and more here in Ohio. Involved in doing stormwater standards and developing agricultural standards, so we've kind of been in the standards business, the BMP business, historically, so kind of a logical fit that way. And then very lucky to have Laura Fay retire from Ohio EPA 401 program and come over here and work with me on this project, that Ohio EPA 401 being absolutely key players in how stream restoration has been and is going in Ohio. And, of course, the funding helps by Ohio Water Development Authority. The projects that fit our criteria numbered 54 around the state with that distribution that you can see on that map. The projects that we looked at were limited to the ones that we called significant stream work. So that's not going to include the kinds of stream restoration work that might be tree plantings or biological manipulation, or certainly not preservation projects, not even stream bank stabilization kinds of projects, but where the channel was actually modified as what we limited our population to. And then also limited them to being more than 3 years old. For that reason, we wanted to look at them as they matured, rather than just as constructed. Got a distribution of the ages of the projects that fell into that population, with about 3/4 of them being 6 years and less, 6 years old and less. you get out to the 11 and 12-year-olds, there's just one project at 12 years, one project 11 years, so that you can see how doing a report like this, doing an investigation like this, really is, it's the time is right for it. The projects were tracked down by looking at a lot of regulatory programs. And another way to break that up or look at that would be to look at projects that were not just regulated but required. Mitigation projects, projects that people had to do. 47 certainly were the bulk of the projects, versus the stream projects that might have been 319 funded, or projects that people went out and picked sites to restore. So projects people had to do versus projects people wanted to do. And they looked about the same to us, so there really wasn't any distinction between the two. It looks like similar work is being done for both of those purposes. So that's the number of projects, 54 projects out there. How do we tell how successful they are? What are the indicators of success? Is no small question, and I don't believe there exists yet a really clear answer to that, not a widely accepted answer to that. There's been a number of papers that propose different ways of looking specifically at stream restoration to determine the success, but I think I can find fault in some of that, or nothing's really come to the top as a widely accepted method for determining that specifically restoration. We've got in Ohio, of course, our wonderful biological criteria tells us an overall stream health, leading the country in developing those kinds of tools. But that's different enough than in the types of projects, the size of the projects, the reason, the site selection for doing that kind of assessment. That's different enough. That overall watershed health, stream health assessment winds up being different enough than looking at stream restoration success. That's not a perfect fit either. So where that left us is going back to the drawing board, back to the basics. In Ohio, we've got early on adopted that very sound idea of ecological integrity, or the integrity of the water resource, to describe this very complex system, dynamic system with lots of pieces and parts, all dynamic and functions and processes going on. I kind of use logically this presentation of the idea of ecological integrity. And I can see if I got a definition here. Yeah, ecological integrity is the integrity of a hierarchy of many simpler functions nested down to individual ecological services. Not exactly the way James Carr presented it, but I think it's consistent with it still. Where we've got these ideas of ecological services that have become much more popular as the kinds of things that streams can do for us, the kinds of things we want streams to do or hope that they can do, like the shaded boxes, nitrogen removal, flood control, or different biotic communities. And those things happen by that nested sequence of necessary steps. We can look at that, for example, the hydrology or the flood control. We can look at that one service that's provided or potentially provided by a stream, model how peak flow attenuation occurs through flood modeling, flood wave modeling, and know that there's a number of things that go into that ultimate how much is that peak flow attenuated. Certainly the rainfall, but also the valley form and the roughness, and all of those wind up being necessary links leading up to how much flood control is provided. Developers not going to do anything about how much rain is falling, but they are going to do something about the floodplain form. So that's what we propose is something that is worthwhile looking at if we want to evaluate the success, is pinpoint those necessary links in these sequences that a developer actually has some influence on, or the stream restoration project is actually influencing. Yeah, what are the variables that are actually manipulated by the restoration? We're certainly not going to do that from one discipline or one assessment technique tool, but the ones that we've got in our toolbox are certainly the stream habitat evaluation, and we perform the HHEI and IBI, QHEI and HHEI. Riparian vegetation can be evaluated a number of ways. We looked at stem densities, different things used in wetland assessment, good vegetative VIBI. Channel morphology is a big part of it. The dimension, pattern, and profile of a stream. The bed materials, of course, different ways of quantifying, measuring all those things, as well as how the water interacts with that form. So we calculated all the peak discharges from very frequent events, the 0.2-year recurrence interval, all the way up to the 100-year recurrence interval storm, and looked to see how those interacted with the channel morphology. And then the riparian soils as well. The soil scientists here at Soil and Water Resources did soils investigations, similar to the investigations that were developed for mapping standards, but modifying one protocol in particular for septic suitability. That method was used and performed on each of the sites, as well as reference sites to see what the natural riparian soils would look like. So those are where all our data came from. And then compiling it winds up being another year-long process. Certainly the easiest analysis is just kind of what types of streams, what are the background variables or driving variables, where is stream restoration being performed. We saw a distribution on the map. Kind of went with population densities. It's being done with land development, kind of the driving force behind when and where stream restoration has been done in Ohio through this first decade and more. And so not surprisingly, fairly short reaches, about 1,000 feet. But again, not much difference with whether it's a stream restoration because someone wants to or because someone has to. It seems like stream restoration still has been done at fairly short reaches. And then small watersheds, surprisingly small watersheds. When I think of streams, I don't usually think of 200-acre size watersheds draining to a stream. And just as surprising is the gradient. I don't know why so many of the streams that are being restored wind up being low gradient, but they certainly are. It may be something to do with the topography or whatever reason is behind that. I don't know, but we do wind up having the streams that have been restored dominated by small watersheds and low gradient streams. Those two in combination, being small and low gradient, if don't match, that's not. We got different stream characteristics for different types of size and gradient, or those two in together. The product of those two values would be really stream power, and stream power is a very telling variable in the characteristics one would expect for a stream. The stream in the picture here was constructed as what one would expect as a typical kind of stream, or a typical water size, or typical gradient, a kind of watershed, kind of stream that we'd expect to have a single thread channel, ripples and pools, the kinds of things we'd expect to see in a stream. but that's not the kind of stream that would naturally form in these unusually small and usually low gradient settings. Not a small number of the sites that we looked at did just what this site did. Is it the constructed meandering channel riffles and pools turned into a meandering thread of wetland, cattails, rushes. To put a little finer point on that, because I think this is one of the probably most important observations of the study, is looking more specifically at stream power. We looked at stream power lots of different ways, unit stream power and total stream power, bank full stream power, and the one that I think is the most telling is this 2-year peak discharge stream power, where it's just a driving variable. It doesn't have anything to do with the bank full or the size of the channel, whether it's big or small. It's just looking at the amount of water coming in during a peak discharge of a 2-year storm and the valley slope. If we look off to the right of this graph, the box and whisker plot there shows all of the named streams in the state of Ohio. So that's where when we think of streams, when the streams are our experience, we've gone out and seen, that's the stream power that we're familiar with, that 67 pounds per second per foot being the median. And certainly a broad range, but that's a pretty small box within that broad range. 50% of the streams are within that fairly narrow range of stream power. The streams that were in the study, the restored streams, there's just a very few of them that would be in the same level of power, similar power to the typical streams we see in the state. A few of them higher, of course, but again, very few. The vast majority of them, the median out here, is 14 pounds per second per foot rather than 67, significantly less than what we see normally. In fact, the data sets that I tried to track down to compare these results with other streams, other work that people have done, just tells us what does 67, what does 14 mean. I could only find one data set that had stream powers that were anywhere near the range of the streams that we look at here, and that was a paper that was done on swamp streams, was what they termed them. And some of these were even below below the range that they were talking about. So that combination of small and low gradient winds up being that we're working in one end of the spectrum of, we got the spectrum of streams that occur in the state. It's very broad, but we're looking at really one end of it as the majority of streams that wind up being influenced, at least to date, by stream restoration. An abundance of examples of them. Another meandering channel, riffles and pools constructed there, and really promptly turning into a meandering strip of cattails. Yet another, and maybe sometime this will become less pronounced as the forest canopy, maybe, if we get wooded corridors around these streams. But while we can plant wooded corridors, we can't construct a forest. So at least initially, there's really no way around having full sun on the projects. And so, but we don't know that yet. Again, these are less than a decade. And the last example here, I'm standing in the channel taking this picture. Laura's on the other side of the channel, and the channel's going on up through there. Again, a constructed single-thread meandering channel. Very typical of streams, but completely wrong fit for this site, the driving variables of this site. Another manifestation of that is in what happens with the riffles that are constructed. There's a little bit higher energy stream here, but one of the features that is constructed often is gravel riffle, and there's probably a bias for larger material in riffles, and cobble preferable to gravel. At least there is for stability. We put in larger material and it's not going to move, and it's going to be a stable channel. And that was very encouraging results of the study. I shouldn't just throw it in as a side point, that it's an important result, that the streams were very stable, that we saw two sites had really much of any indication of incision. So a critical aspect of doing the stream restoration work, and we were seeing very little of the incision. But and maybe that's in part due to these riffles that are constructed with coarse material, but there is a drawback to that too, because I would imagine that one of the intentions of constructing a riffle is to be producing riffle habitat at those interstitial spaces where things live. And this is a rock that I plucked up out of that gravel, or the cobble riffle, which was the norm. It's not just one that was plucked out that looked this way. That line there, that black, was below a layer of silt and fines that seal it off, completely anoxic and no interstitial habitat in there. So they look kind of nice from the top, but once you really look at them, they're not much, not a functioning riffle that would be mobile during high flow events. Maybe that's something we have to live with because of the stability being so important, but it is certainly something that's happening out there, is that the riffles that are being constructed, well, they may be performing some good stability, having some good stability success, they're not generally being effective riffle habitat. Another riffle, I'm taking this picture while standing kind of across a pool and looking at a riffle. So there's the riffle going upstream, and the coarse material that was placed for the riffle catches the fines. The fines settle in that and create real good area for the vegetation to colonize. So having kind of wetland characteristics to the riffles and maybe open deep water pools. This one's dry, of course, at the end of the year, but during the spring that would be a deep water pool. And then whether good or bad, and maybe that's kind of interesting habitat. Maybe we're getting some good processes going on in there. Maybe that's good for denitrification and certainly roughness, and it is providing some kind of habitat. But that isn't a definite observation. That it's unintended, I'm sure, from the way they were designed and constructed. And unfortunately, while this one may be just fine, it's probably not the most efficient way to produce the kind of results that we are seeing. There's a lot of expensive rock that gets buried with fines. This is an example of probably what is a more appropriate fit to the very low energy environment, where you can see that just a 166 acre watershed, and the developer wanted to move this ditch over, going through the middle of the site. So got a 401 permit and constructed, I think, certainly a narrow, but I think a system that is similar in type to what it would have existed there prior to the ag ditch that was constructed across there to dry this site out. It's probably a wet meadow kind of environment. The soils on the site are not alluvial soils. The soils are more wetland, hydric soils, but non-alluvial. The stream power, the soils, the topography lead me to believe that this was or that what we see now is similar to, it's restoring the form and function appropriate for this environment, for the driving variables. Another big aspect of channels, as far as those critical links that lead up to that in that nested sequence, important for a lot of the ecological services that we see along the bottom of that first, necessary for a lot of those ecological services, would be floodplain form. For self-purifying sediment deposition on floodplains kinds of processes, to habitat, to flood routing, so the mixing, the roughness, the storage, the height, and the extent of floodplains would all be variables that we can measure that are influenced by developers and are necessary links leading up to those ecological services that a stream does or does not provide. We did another important graph, so bear with me on this one. I think this is an important point to spend a little time on. But I mentioned we looked at each one of the sites, surveying the geomorphology of it, and then finding the peak discharge of all of those different flow events, from the very frequent to the rare. We did that, and we did that because we didn't have an indicator of floodplain connectivity. I don't even know of a definition of floodplain connectivity that satisfactorily describes the quality of the different floodplains influencing those processes. Certainly something like the entrenchment ratio that's used in the classification system, Brosgans, it's too coarse of a measure of the floodplain form. Bank height ratios, they didn't get anything. They weren't looking very promising. So we went in and developed this number, the floodplain connectivity number, which is basically the exposure of the floodplain to floodwaters. It's acreage of, or a square footage of, area that's inundated. So a square foot gets inundated once, that's 1 square foot of exposure to floodwaters. So we look at the area that's inundated by a frequent storm times the number of occurrences of that storm, gives us a cumulative area over a 100-year span of time. Got that? Cumulative area of water exposure to the floodplain surface over a long span of time, which means nothing by itself, but we can compare it to a kind of reference condition, which is finally what we have in this graph, that 100% would be a floodplain of kind of a typical width, typical natural width, and a typical height. And if we did that same exercise of all of those different recurrence intervals times the number of occurrences, we would get a value for that site. And that's what is plotted here, or that's what the 100% would be here. And all of these lines are how the individual sites compare to that kind of standard reference point. And then we can see it's great that we've got a number of sites that are really up to outstanding as far as the amount of floodplain processes and exposure goes compared to natural streams. And then the bulk of them would be between, well, something less than 100% down to kind of a minimal amount of what we'd expect in natural conditions. And then way too many of them in that red range there on the left that would be described as a highly entrenched stream, very limited floodplain, unstable, and probably poor quality habitat would be associated with a very limited amount of floodplain that you'd see described by those far too many sites. So on one hand, it's encouraging to see the range. We know that if maybe this is showing us that it's possible to get good quality floodplains, but it's a bit surprising that it's such a drastic range.
Dan, quick question from one of our participants. Catherine Skalick asks, what's the range of recurrence intervals that were used to develop the floodplain connectivity data?
0.2 year to 100 year. And going halving scale, so 100 year, 50 year, 25 year, 12.5, all the way down to 0.2.
Okay, thanks.
Example of one of the poorer sites as far as floodplain connectivity goes. That blue line that we see in the cross section is showing where we would expect and where we saw indicators of a bank full or where a natural floodplain would form. And the red line up there, a rare flood event, but that should be out over an extensive floodplain. So if that's the appropriately sized channel, we would expect the blue line and definitely the red line to be over a wide, several times wider than the channel area, and it's simply not the case. The channel was constructed, natural channel design, a meandering channel and riffles and pools constructed, but I can't imagine that the floodplain was on the radar or entered the thought process of the designer that was working on this. That it just, whatever the channel design was that he was trying to achieve, I don't think that included any desire or goal or criteria for providing floodplain connectivity, not even on the radar. Another example of the same thing, that you're an ODOT site with all kinds of room and this interchange, and the blue line here again is the frequent floods, and expect the floodplain to be about at that stage. Nice to see some even lower ground within that area, but it's not it's got some width to that, but there's so much more width that wasn't taken advantage of. It's just a foot out of reach, or it's just 2 feet out of reach. So we've got this area, this site that's 250 feet wide and hardly 50 feet of floodplain that is taken advantage of. And it's almost painful to look at because it's so close yet so far. It could have easily provided a lot of floodplain connectivity and all of those services and processes that would have resulted if only they had wanted to. That red line up here is a 50-year recurrence interval storm, and so half of the site is taking advantage of this floodplain once every 50 years. So that's just a shame. So close yet so far. Well, figuring out the peak discharge of all those different recurrence intervals is, I think, a really good number. It's describing the actual processes and it's describing the exposure of water to the floodplain surface, but it's not very practical to use. I mentioned the entrenchment ratio didn't correspond to that very well at all, but we did propose this scheme of looking at the floodplain widths at 3 different stages, and then giving those areas that would be inundated at each of those different stages kind of a diminishing weight with height, so that we can give us a value there and correspond well with actual floodplain connectivity, that process. And I think it's a practical way for asking for floodplain connectivity. That huge variability that we see on all those sites, I think it's simply that, well, in part due to we just haven't asked for it. So this would be a way to ask for it in a quantifiable way. That's has been in the draft EPA mitigation rules up until recently. I hope it's still in there, and I think there's if anybody from EPA wants to weigh in on that with a comment, but I think early next year we're going to know whether that's going to move forward or not. Another discipline or another area that we look at is floodplain riparian soil quality, and that the soil scientists, again, doing this investigations of the sites as well as reference sites to describe the things that they do describe, the different horizons and the organic matter, the roots, the soil structure, those kinds of things. Also, we're doing the soil permeability tests here. We're seeing what infiltration rates were, water moves through the floodplains, to get some good numbers on those. And getting bad numbers on other sites that while they're like the floodplains that had a tremendous range from extraordinarily good to very bad, the soil quality also had a tremendous range to very bad, as we see here. Maybe this slide is actually showing very bad as both floodplain extent and size, as well as soil quality. Laura is standing there just about to step down onto the floodplain surface that was permitted as a meandering channel with a floodplain and riffles and pools and a forested riparian corridor. There's a forest that you can see some more forest up here. That having not just a subjective description of meandering channel with a floodplain, but having that quantified as the floodplain height and extent, as well as being able to quantify the soil quality, seem like it hasn't been a part of many of the projects that we've looked at, a significant number of the projects that we looked at. The results of the soil scientists were, well, a tremendous amount of data that they produced and then analyzed it in a number of different ways, and none of it's very clear. Let me try this one, where we ranked all of the sites with all of each of their characteristics. So organic matter is easy, the highest organic matter to the worst organic matter. And we did that for each of the variables that we see here, the horizon. So A horizon is better than B horizon, and C horizon would be least good. Root density, of course. The consistence, or how loose it is versus how firm, and the permeability. So if we look at the rankings that each of those characteristics would have on our sites as well as our reference sites, and take all of the characteristics and compare it to each other characteristic individually. So if we can look at the horizons, we can look at how the horizons were ranked, the best horizons versus the worst horizons versus the reference horizons. Lots of A horizon, a little bit of B horizon, and some C horizon, very little C horizon. You can see how that compares to the ranking of the sites based on all of the other variables. So this best column is the best sites or based on organic matter, consistence, permeability, and root density, everything else. So this tells us how well horizon corresponds with everything else, all the other aspects of it. And a conclusion that can be drawn from this is that, maybe not a surprising one at all, is that the different variables have a strong correlation with each other. That pretty much we see good root density when we also are seeing high organic matter, lots of A horizon, and fairly loose soil with high permeability. And shows up, that same thing shows up again if we look at the average of all of the characteristics. We can say that the best soils are similar to normal natural reference riparian soils, and are drastically different than the worst of the sites. Yeah, there we go, drastically different. Neil Martin, one of the soil scientists, probably put it as clear as anybody could when we were first exploring the different sites and wondering different methodologies we might use. He said that the difference between the two sites that we had just gone to was the difference between night and day. Which doesn't do us any good at all. I'm saying one of the sites we want soils that are good soils, or we want soils that have high root densities is, well, that's like saying that we want developers to build us nice streams. There's got to be some way to quantify it. There's got to be some way of saying up front which kinds of situations to avoid or which kinds of situations should be encouraged, so that the result is soils that have high permeability, organic matter, and consistence. Well, this is an effort to do that. One approach to doing that. What we have is a plot of all of the sites from those kind of hard soil scientist numbers, ranking them the best sites to the soil scientist, the organic matter, consistence, all those things, to the worst sites. And then what we see on the bars is the percentage of different variables that are actually definable at the design stage. And that's good, because we see a lot of those variables on the left and we see a lot of other variables on the right. So the red is probably things to avoid and the blue is probably things to encourage. There's the organization of those ideas. So on the encourage side, the recent deposition, or the create conditions for self-forming soils, whatever those would be. We see point bars, high-quality soils. We see soils that just have a lot of accretion, are high-quality soils. Soils that reconnect to the old floodplain surface, not the soils that are down at a lower stage, but if there's the old surface, maybe a dam removal kind of project where you've got a flat surface to the old soil, maybe the stream's an entrenched stream in there, but picking up an entrenched stream and reconnecting it so that it's appropriately proportioned with the surface of the old soil reliably describes those high-quality soils. Avoiding poor resoiling material. So even if material was excavated and replaced, if it was poor material, it seems at 6 years anyway that there's little improvement and the site limited by those poor resoiling materials. So the quality of soils have to be good, top quality topsoil rather than other kinds of resoiling material. And then, unfortunately, too many of the sites are constructed out of the material that would exist in the soil horizon at a lower elevation, a deeper elevation, away from the surface and the organic layers up top. But if the stream's down at a lower elevation, or if the stream's been moved into a hillside, there's a lot of excavation down into the subsoil, and the floodplains are constructed out of that material that exists in place there. And that very reliably describes the worst of the soil quality, that those characteristics the soil scientists were coming up with. So those four, that's one approach anyway. Maybe there's others as well, but that's one approach to encouraging conditions, encouraging high-quality riparian soils and discouraging poor-quality riparian soils. So, in conclusion, we started out with one question, how are we doing? And now we've got a number of questions, which are a number of answers and lead to a number of more questions. So that's good job security. restoration has been done principally by mitigation. That's certainly not the only way that restoration could be accomplished, but kind of looking at these conclusions, that's certainly something to keep in mind, that that's how mitigation work. The projects that we looked at have come to be, is someone's been forced to do it by mitigation. And it's been done at fairly short sections, and it's been done at the rate that Walmart's and Myers and ODOT have been manipulating streams. The scale that they're doing that is nowhere near the scale of the streams that are out there previously modified, would stand to have a lot of potential for restoration. So leading to if that's how mitigation, if that's how restoration has been done, the question is there other mechanisms that can bring about restoration that would be more in line with the scale of the restoration potential? What other mechanisms can restoration be accomplished? For example, we owe the restoration that's occurred to the 401 program and Army Corps of Engineers 404. What has the stormwater management industry, bureaucracy done, especially on these small streams that it's even hard to call them streams, in that very small part of the watershed? Is there any potential there for affecting many more miles of streams through a whole other group, a whole other institution? Agriculture, how to describe that more, thousands of miles, hundreds of miles. That is there a way to bring that, influence that, so that it would be causing more stream miles to be, so that we're not just talking about what we are looking at now, which is a drop in the bucket. The stability of the streams, the restoration has produced some very good stable streams, but kind of at a cost. The streams are just so forgiving, and how much do we want to restrict them or hem them in? How much do we want to construct a finished product with some of that coarse material that we see, versus how much can we reinitiate the dynamic processes that streams would naturally have? And maybe a number of ways of doing that. I'm not sure what they all are, but there does seem to be a limitation on doing kind of over control of or payoff with that versus the freedom that the processes, the evolution of the channels. And then the streams certainly need to fit the landscape. Restoration has been making streams that are typical riffle pool meandering channels, and that's not where restoration has been occurring. So can restoration be done? Can it be influenced so that can it be sensitive to the be appropriate for the landscape? Can projects be judged relative to the best fit conditions? I know that there's some real problems that have been discussed with that from the beginning of the discussions about these kinds of things, wetlands versus streams and the different regulatory programs, and it might be some hard questions to answer there. And lastly, the restoration work frequently has produced poor floodplain connectivity and poor riparian soils, those two areas. And what needs to happen so that we don't see such a range of great soils and great floodplains to extremely poor? How do we improve the odds of getting better characteristics in both of those areas? Oops. There we go. The report is available on the DNR website. You can contact me if you would like to download the whole report, and I can help you negotiate the DNR website to actually get to this point. One of the more interesting things about it is the photos that are available from each of the sites. You can kind of quickly go through all of the sites, show you. There's a map here as well, but go back to that. Photos. Got these photos set up. Just going through the slideshow of these gives you a good idea of the projects that I didn't show you many of today, but seeing all of the projects presented in this way is a real quick way to get a good feel for the kinds of streams that are being influenced, the kinds of projects that have been produced, and then I've also got some of the key quantities down there at the bottom. And there we go. Thank you.
Okay, thanks, Dan. We've got a few minutes left before 1. If anyone has any questions they want to type into the chat box. I also want to call everyone's attention to the chat box where Brian has put in a link to the evaluation. We very much appreciate everyone who fills out the evaluations. Helps us to to think about future programming and gives us feedback on the format and things like that. So please do click on the link before you leave the WebEx and fill out the evaluation. And again, any questions, please feel free to type them in. And in the meantime, Dan, I have a question for you. Since so many of the sites that you looked at were very small streams, they have very small drainage areas and very low gradients, do you see that as a weakness in terms of the restoration or the mitigation projects that are getting done, or do you see that as that's just what's available, that's what the majority in the areas where mitigation is being done, that's mostly what you're going to find, and we just need to do a better job of matching up the type of restoration that we're doing with that type of stream? Or would you rather see a greater diversity of sizes of drainage areas and gradients?
Well, I don't think it matters much what I think, because they are what they are. I think the first point is that we can't argue with those variables, the driving variables. So the only thing we can do is do things that are appropriate for them. On the other hand, if we stop and think about it for a minute, maybe it's not a bad thing that maybe there are advantages to having some of the low-energy streams, or more of the low-energy streams. They probably do more than their fair share of kind of BMP work, or the assimilative capacity of lower gradient streams is probably a bit higher than higher gradient streams. So maybe that's a good thing, not that we're going to do anything about it. But I guess so far third point is, so far we've gotten pretty much the streams that people have been messing with. And maybe that's good that people are messing with streams in areas that already have been messed with. Maybe those are streams that are in most need of restoration. I don't have those values, but I kind of suspect it is. If it's not, then maybe we could take a more objective approach or strategic approach to identifying what streams should be restored, whether high energy or low energy, or what, and picking out those sites instead of just being taking whatever's wherever Myers wants to build a store.
And we got a question from Kurt. He's asking, given the size of these restoration projects, is it reasonable to expect any improvement in downstream water quality or aquatic life?
Well, I would like to say I could provide numbers to say exactly what that improvement would be. I think I will be able to provide numbers, just good estimates of kind of per foot improvement in maybe denitrification or phosphorus uptake or sediment accumulation. We can take a stab at some of those already, and maybe defining significant is where we get the wiggle room in there. But I think it will be possible, and I think we will be able to describe the percent improvement or the pounds of those kinds of things that are assimilated within 1,000 feet or per every 100 feet or whatever the units we use, and then with that information decide whether a project would be, whether it would be worth maybe adding water quality money to a project, maybe an agricultural ditch project that would be performed for a certain cost, could be performed in a different way that would provide some services. It's hard to say that we should step up to the plate with water quality money and have it done in a different way if we really don't know the answer to your question. So coming up with that answer, I think, is a pretty high priority around here, and I'd say within a year we're going to have hopefully some user-friendly tools to be able to describe just what those are, so good decisions can be made with an understanding of quantified improvement per project.
And last question from Greg, is there a stream power threshold where a channel should be restored as a stream or a wetland? I think he's asking, is there sort of a breaking point there where below a certain power we'd be talking more about more of a wetland kind of environment versus a free-flowing stream environment?
10, 15, maybe that threshold is 10 pounds per foot per second. Maybe it's 15. Maybe it's even a fuzzier line than that, depending on like maybe early succession versus later succession. We have trees growing up around it. Maybe you get a single thread forming more within that kind of environment. And the amount of bed load would be another amount of coarse material or even sand that would be moving through a system would be another variable that would make that line a bit fuzzier. But yeah, I think that they're kind of the ballpark would be a threshold of around 10. Yes, there is a threshold, and it would be somewhere around 10 or 15.
Okay. We did have one more question from Jeff Boyles. Dan, I'm going to let you address that to him personally, your response to that, because I want to be respectful of our time. And thanks a lot, Dan, for presenting. Thanks to all our participants for being on the WebEx. And please do fill out the evaluation. And we hope to have the recording of this webinar posted within the next couple of weeks. In the meantime, I certainly would encourage folks to go to the ODNR Division of Soil and Water Resources site, find the report from Dan, and take a closer look at it. There's a lot more in there that Dan couldn't cover today, but I think it's a very important, very interesting report for those of us who are thinking about what's the best use of our money in restoring streams within our watersheds, and how do we think about what's a successful project and what types of projects to prioritize and things like that. So very, very interesting, important study. So thanks, Dan. I'll let everyone go, and Dan,